Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics 3, RLT College of Science, Akola. Dear student, in this lecture we will see non-Poisson model number 3, that is MG1 infinity GD model. So in previous lecture we have seen non-Poisson system model number 1 and 2. So in this lecture we will see third model, that is MG1 infinity slash GD. So this model consists of a single server, Poisson arrivals, and a general service time distribution. In this case, the probability that customer leaves the system in t, t plus delta t is a quantity dependent on when the service of that particular customer begins. That means we can say that they would involve not merely t, but also another time variable, say t dash, measured from the beginning of the current service. So let us we consider q0 be the queue length when the service of the customer n terminates, and q1 be the queue length when the service of the customer n plus 1 terminates. Also, let us suppose that for k equal to 1, 0, 2 and so on, denotes the number of customer who arrive during the service of customer n plus 1. Then we can have the following relations between q0, q1 and k. So it is written as q1 equal to k if q0 equal to 0. That means we can say that the queue length is 0 after serving the nth customer. Second, q0 minus 1 plus k, where q0 greater than 0, that is the queue has q0 units after serving nth customer. Okay, so these are the two relations together can be written in the form of q1 equal to q0 minus delta plus k, where delta is 0 if q0 equal to 0 and delta equal to 1 if q greater than 0. Thus the expected value of the above relation can be obtained as E of q1 equal to E of q0 minus E of delta plus E of k, where E of q1 equal to E of q0 in the steady state equation. So it will follow that estimated of delta equal to estimated of k, that is E of delta equal to E of k. Also further that q1 0 equal to q0 minus delta plus k bracket square. So if you take the bracket, if you take the square, so you will get q0 square plus delta square k square plus 2k0 minus 2k delta minus 2 delta 0. This is delta square plus k square. Okay, not a into. So this is a plus sign. But by the definition of delta square equal to delta and delta q0 equal to q0. So we will get this equation we will get, that is q1 square equal to q0 square plus k square 2k q0 plus delta minus 2k delta minus 2 delta q0. So therefore expected value of this equation can be written as E of q1 square plus E of q0 square plus E of k square 2 expected of k q0 plus E of delta plus E of k delta and minus 2 E of q0. Again we know that since E of q1 square equal to E of q0 square in a steady state equation, then this equation, so we will use this equation, we will use this term in above equation. Then this equation can be written as 2 times of expected value of q0 minus 2 e k of q0 equal to e of k0 e of k square plus e of delta minus 2 e of k delta. Okay, so that after solving we can find out e of q0 equal to e of k square plus e of k minus 2 e square k divided by 2 times 1 minus e of k. Since e of k delta equal to U of k, U of delta, where U of delta equal to U of k, and Q0, k and delta are the independent. So here, if delta means the arrival rate and the number of arrival in a service time of length is t, has a Poisson distribution with a mean lambda t. The probability of k arrivals in a time t, therefore it is given as lambda t to the power k e raised to power minus lambda t upon k factorial, where k greater than or equal to 1, and the probability of the k arrivals during the service time of the customer is given as integral 0 to infinity lambda t to the power k e raised to power minus lambda t k p of t dt, where p of t is the probability density function of the service time. So now here we will find out the number of the arrivals in a service time of a customer, and it is given as E of k equal to lambda E of t, and we know that E of t equal to 1 upon mu, where mu is the mean service rate. Second, the variance of the arrivals in the service time of the customer is given as expected value of lambda square equal to lambda E of t plus lambda square E of t square. Okay, so here E of t means service time, and U of t square means variance of the service time plus square of the service time. Okay, so this can be written as lambda divided by u plus lambda square sigma square plus 1 u square. So after solving we will get rho plus lambda square sigma square plus rho square. So substituting the values of u of k and u of k square in the equation eq0, in this equation eq0, then we will obtain from this equation u of q0 equal to putting the values, we will get rho plus lambda square sigma square plus rho square divided by 2 times 1 minus rho. Okay, so also if the customers n plus 1 has a no wait for a time omega before being taken into service, then the length of the queue must be q1 during the time omega plus t. So therefore expected value of q equal to lambda omega plus r, and it is written as lambda e of lambda omega plus lambda e of r. So here lambda e of omega means average waiting time, and it is written as e of q minus lambda mu. So therefore e of omega equal to taking lambda dividing on both sides lambda, so 1 by lambda. Okay, so after solving this we will get lambda square sigma square plus rho square upon 2 lambda upon 1 minus lambda. So here since E of q1 equal to E of q0 in a steady state, okay, so therefore we can summarize the various formulas for mg1 infinity gd as follows. Average number of customers in a system, that is lambda square sigma square plus rho square divided by 2 times 1 minus rho plus rho. Second, average queue length, that is equal to lambda square sigma square plus rho square upon 2 times 1 minus rho plus rho minus rho. After solving we will get lambda square sigma square plus rho square. So this row and this row will get cancelled, only remaining this term, first term. Then average waiting of the time customer in the queue is given as same. Okay, only here is lambda is additional term. Average waiting time that customer spend in a system, that is lambda square sigma square plus rho square divided by 2 times lambda 1 minus rho plus 1 upon mu. Okay, so here these are the some various formulas for the mg1 infinity gd model. Now we will see some problems on this model. So first problem is, at a certain healthcare center, patients arrive at a mean rate of 4 per hour, and they are checked by a doctor at a mean rate of 5 per hour. The center feels that service time have some unspecified positive skewed unimodel to tailed distribution with a standard deviation of 0.05 hours 3 minutes. So we have to find out determine the queuing characteristic for the healthcare center. Second, how much the assumption of the exponential service time would distort these values. Discuss. Okay, so we have to solve this problem. So we will find out the data. We will write down the some given terms which I already given in this question. So here we have given mean rate of patient, that is lambda. So lambda equal to 4 patients per hours. Okay, and mean rate of check, that is mu equal to 5 patient rate per hour. Okay, and sigma is given as, that is standard deviation 0.05, and rho is 4 by 5, that is 0.8 hours. Rho we can find out lambda by mu 4 by 5. Okay, so by using this formula, lambda by mu mean that is rho 4 by 5, that is 0.8 hours. Okay, so for the single server model with the exponential arrival and general service time, the values of the various queuing characteristic will be as follows. So first we will find out the average queue length is given by formula, that is E of m, that is lambda square sigma square plus rho square divided by 2 upon 1 minus lambda. So putting these values in this equation and solving, we will get 1.7. Therefore, average waiting time in queue is given as E of m upon lambda. So E of m is 1.7 divided by 4, that is 0.425 hours. Then average number of patients in a system is given as E of m plus rho. Putting the values of E of m plus rho, we will get 2.5. Then average waiting time in a system, that is E of m upon lambda. We know that E of m, that is 0.425, and lambda means plus lambda is 4 and mu is 0.2. So after solving, we will get 0.624 6 to 5 hours. Second, if the service time follow exponential distribution, then the result obtained as follows: E of m equal to 3.2, E of w equal to 0.8, E of n equal to 4, and E of v equal to 1. By using the formulas and putting the above values, we will get this result. From the above, we can observe that the patient's waiting time and the number of patients are more as compared to the previous case. Okay, so this is the first example on a model number 3 MG1 Infinity GD model. Now we will see the second example. What is the second example? The given that in a heavy machine shop, the overhead crane is 75% utilized. Time study observation gave the average slinging time as 10.5 minutes with a standard deviation of 8.8 minutes. What is the average calling rate for the services of the crane? And what is the average delay in getting service? If the average service time is a cut of 8.0 minute with a standard deviation 6.0 minutes, how much reduction will occur on average in a time delay getting served? Okay, so this is the MG1 Infinity first come first service process model. Okay, so here we have given rho is 0.75% utilized, mu is lambda by mu is lambda by uh, lambda by mu, that is 60 divided by 10.5, that is 5.75 per hour. Lambda is rho plus mu, that is 4.29 per hours. Okay, so therefore the average delay in getting service is given by U of W equal to by this is the formula, given formula. So here we have given rho, mu, lambda. Okay, so putting these values in this formula, we will get U of W equal to, after solving, we will get 26.8 minutes. Then if the service time is cut to 8 minutes, then mu is 60 divided by 8, that is 7.5 per hours, and rho is lambda by mu, that is putting the value of lambda and mu, we get 0.571. Our utilization of the crane reduced 57.1%. Then putting the values in this equation, we will get U of W. Put all the values, we will get 8.3 minutes. Therefore, a reduction 18.5 minutes of or approximately 70%. Okay. So this is the required solution of the given problem number 2. So in this way, we have completed model number 3. Okay. With example 1 and 2. So with this lecture, dear student, with this lecture we have completed all the syllabus, all the unit of unit number 4, as well as all the syllabus of MSc second year operations research paper. So in with this lecture I will conclude that I will declare the operations research syllabus here is completed. So I am very thankful to all of you dear student. You have listened carefully and watched my all videos, and you are doing very well. So I am very thankful to all of you. So I will declare from this lecture the operation research syllabus is totally 100% completed.